I thought I'd start off today with a little review. In the last lecture, there were an awful lot of new terms and words that were thrown out. And I don't know about you, but when I see things like that for the first time, I have a very difficult time remembering those things. So especially if there's some relationship between one and the other. So I thought it would be worth our time here to spend, just go back and review a few of the things we've already talked about. So let's go all the way back. Let's go back to the original picture we had of the structure of the Earth that was created from the protoplanet. The structure of the Earth, of course, threefold. You have the core. Now, the core is basically made of iron, molten iron. Well, actually, it's probably iron and nickel, but basically iron. Remember now, that's the most abundant metal in the universe. It's molten, except for perhaps the very center of it. There's still an argument as to whether the center might be solid, or perhaps if it's not solid, a very, very viscous liquid. But the core is made of the iron, and the average density is supposed to be about 15. Then surrounding the core now, we have the great mass of Earth, which is called the mantle. The mantle is made up of a rock called peridotite. Peridotite is an iron-rich rock, not as iron-rich, of course, as the core, but it has enough iron in it that the average density of the mantle is about 6. So note 6 floats on 15. And that's an important concept to get across, is that at this scale, we're talking density separation and floating on each other. So the mantle literally floats on the core. Now, some people think the very bottom of the mantle could actually be a mixture of oxides again. In other words, down there, the temperatures and pressures are so high that maybe even the peridotite decomposes into its respective oxides, aluminum oxide, silicon oxide, iron oxide. That's a theory, but I'm not sure whether it's true or not. Then finally, on the very outside, we have that outermost brittle layer that we call the crust. The crust, now averaging about 40 miles thick, is made up of two components. We have the oceanic crust, which is made up of basalt, and then we have the continental crust, which is made up of granitic rocks. Now, I say granitic rather than think granite itself, because the fact of the matter is there are two rock types. There's granite, which you all know, or heard about at least, and then there's another called granodiorite. Actually, not many people can tell them apart, and so they look very much similar, so we just sort of group them all together and simply call them granitic rocks. So that's basically what the continents are made of. Well, anyway, that is what the picture was for a long, long, long time, until we came up onto plate tectonics. Now, just beforehand, we had a discovery made by the seismologist that said that, well, the structure isn't quite as simple as that, as mantle crust. They said they had discovered down below the surface this layer from about 100 miles down to about 250 miles down that was special. It was different from the rocks above and below in that these rocks were plastic. Now, what plastic means, remember, it's a solid, there's no doubt, these are rocks, but they act like liquids. Now, what liquids do that rocks, solid rocks don't, is they flow. So here's that layer now we're going to talk about in a moment, where all the convection cells are. So that's the asthenosphere. Now, above the asthenosphere to the surface is a layer that they call the lithosphere. Now, the lithosphere is brittle, and it means what it says. When you do something to it, it's going to break. But remember now, this is important, that the lithosphere is not just the crust. The lithosphere is composed of the crust plus the outermost portion of the mantle. So it's actually a combination of mantle and crust that makes up the outer portion of this lithosphere. Well, back to the asthenosphere now. The asthenosphere is the place where all these convection cells are. This is supposedly the source of the energy and the mechanism we're going to use to break the lithosphere apart. Now, I think it's important to really understand these convection cells. Now, sure, you know what a convection cell is, but I want to go sort of through this thing of convection cells just to make a point, or several points, actually. So let's talk about convection cells. The simplest example I can think of, you put a pot on a burner on a stove. You take a beaker of water and you put it on a Bunsen burner, and it heats up the water. As the water heats, of course, it expands, density goes down, rises to the top of the pot or the beaker, flows out of the top, cools, density goes back up again, becomes heavier, and it goes back down the sides to be reheated. So basically that's a convection cell. And any watching of a boiled pot of water, that you see the convection cells. But now what I want you to do is consider something a little bit different. What I want you to do now is consider a fish poacher. Now, I don't know if you know what a fish poacher is, but it's a pot It's about that long, it's about that wide, maybe that deep, and it's designed so you put a whole fish inside it to poach it. Now, see, I know all this stuff because I do all the cooking in my family. But anyway, that's what a fish poacher is. Now, it's too long to put over top of one burner, so usually you put it over top of two burners. So the picture now is a fish poacher with the water heating up, but you got two sources of heat now. Over each source of heat, you have a convection cell rising to the surface, going out on the surface, cooling and back down. But note you have a convection cell over each heat source. And now this is very important too. Note within this convection cell system, you have a rising portion of convection cell and then a downgoing portion of convection cell. Rising portion of the convection cell. In other words, they alternate like that. Rising, sinking, right? You never have two rising portions together. That's impossible. Nor do you have two sinking portions together. They always alternate like that. And that's sort of an important point to be made, I think. Now, here's the next thing I want you to do. I want you to picture taking a slab of wood and cutting it to fit the inside now of this fish poacher and put it down on the water. Now, obviously, it floats. Why? The density of the wood is about 0.5. The density of the water is 1. Light things float on dense things. So here's this piece of wood now floating on this water in its fish poacher with these convection cells coming up underneath and going back down again. Now picture this now. The water coming up underneath the wood, rising portion, spreading out underneath the wood plank, and it sort of pulls by drag on the wood. Well, that kind of thing like that, that's tensional forces. So above the rising portion of the convection cell, you generate tensional forces within this slab of wood. Where the water is coming together to go back down, you have compressional forces being generated in the slab of wood. So note, they alternate. Tension, compression, tension, compression. You cannot have two tensional zones next to each other, nor can you have two compressional zones. It always alternates. Tension, compression, tension, compression. Now here's all I want you to do. Very, very simple. All I want you to do in your mind is to change that slab of wood to the lithosphere. And I want you to change that pot of water to the asthenosphere. And then I want you to change those two burners on your stove to two heat sources coming up from below, from the center of the earth. Everything else is the same. You have convection cells now within the asthenosphere, rising up underneath the lithosphere, creating tensional and compressional forces within the lithosphere. Now the lithosphere is brittle. What it means is if you try to do something to it, pull it apart, jam it together, it's going to break. So now we're going to break things. Okay? Let's take up the tensional forces first. What we're going to do now, we're going to take the lithosphere and break it. We're going to break it at the tensional forces and at the compressional forces, and we're going to break this thing now into pieces. Remember, the pieces now are going to be called plates. But let's talk about the tension first. We're going to talk about taking a rising portion of a convection cell. We're going to bring it up under the lithosphere, but important now, this lithosphere is a continental lithosphere. In other words, the rising portion of the convection cell is under a continent. So we're talking granitic rocks here in the crust. What's going to happen? Tensional forces are going to be generated within the crust, within the entire lithosphere, and it's going to break. What you're going to see from the very beginning are cracks starting to form from the bottom of the lithosphere, working their way toward the surface. Now, once they get to the surface, then they're going to line up. And so on the surface, what you're going to see is a series of cracks opening up under tension. We call that force, that pulling apart, rifting. So we'll call this a rift zone. And so the rift zone starts to develop. Now, the next thing that's going to happen, back down to the asthenosphere, at the very top of that rising portion of the asthenosphere, right at the top now of the asthenosphere, this layer of rock that was acting like a liquid becomes one. It melts and creates a magma. Now, unfortunately, we don't have time to go into the mechanism by which magmas are formed, so you'll have to take my word for it. But the magma that forms is always basaltic. Now, remember, that's the lowest viscosity of all. It's the one that flows most readily. And so what happens, once this magma, this basaltic magma forms, it starts to work its way up through those cracks. Somewhere along the line, once it gets into the continent, it's going to run into water, groundwater, which we'll talk about in another chapter too. But it's going to run into groundwater, and the groundwater is going to become heated, and the groundwater is going to rise to the surface. So along this rift zone now, what you're going to expect to see, you're going to expect to see things like hot springs. Some places the water actually boils. And so out of these cracks comes steam squirting up in the air, and we call those fumaroles, and we'll talk more about those when we get around to talking about volcanoes. And the other thing is, sooner or later, some of this basaltic magma can come to the surface to become basaltic lava and flow out to form lava flows. Now, these are not going to be any great lava flows. This is not going to be like the Columbia Plateau. These are fairly small little lava flows, and maybe even there's enough gas left in the magma when it gets to the surface to blow some of the molten rock up in the air. We call those fire fountains, maybe 1,000 feet, maybe 2,000 feet at the most. And as it blows up in the air, it breaks into little pieces which solidify on the way down, and those little pieces then become what we call cinders. So the cinders accumulate around the point where all this is coming out into what we call a cinder cone. So the point is that this zone now, this rift zone, is volcanically active. What does it mean? Well, what it means is we're talking about a continent starting to break up. Question, can I send you someplace to see a place like that? Yes, I can. I think all you need to do is go to Albuquerque. Coming up out of Mexico, right up through the center of New Mexico, right through the suburbs of Albuquerque, on up through Los Alamos into central Colorado, you have a zone just like that. And you can go there and you can see little lava flows, and you can see hot springs, and you can see cinder cones. I don't think I've ever remembered seeing any more fumaroles there, but you can see the volcanic activity. In other words, it's still going on. Now, question is, does that mean that North America is breaking up? Well, I was on a field trip to the rift last summer, and I talked to the people who were leading the trip, and I asked them, that was their bag, this particular rift zone. It's called the Rio Grande Rift, by the way. The reason why is because the Rio Grande River follows it for a while before it heads down to the Gulf. So I asked them, is it meaning that North America is breaking up? And they seemed to all be of the opinion that it was not. They called it an aborted rift. In other words, the idea is if nature had continued on, yes, it could have split North America up. But apparently this rift started, it developed, and then it sort of died. It's now aborted. Whether it comes back or not, we don't really know. That's something for the future to tell. But the whole point is, when continents break up, that's what they look like. You form the rift zone first. Now, step number 2. Here's all you have to picture. Now, I used to do this when I was teaching the small classes to demonstrate the following. You know those flat party cakes you get, just one layer and on a piece of cardboard? I used to have a bakery make me one and put it on one piece of cardboard, but put it then on another piece of cardboard, budding 2 pieces, and put the cake on top of that. And they never understood why I wanted to do that, but I said, just do it. And so what I did in class, and remember that icing that's on it? It's like glass, but it solidifies. I took those 2 pieces of cardboard and started pulling them apart. And the first thing that they saw were the cracks forming in the icing. That's the rift zone, see? So here's your rift zone forming. And now I just want you to visualize this in your mind. As you continue to pull that apart, what happens is the cracks get bigger and bigger. And pretty soon, that central part of the cake where the rift zone was starts to collapse on itself and forms a valley in the cake. Well, since it's a rift valley, we call it a rift valley. Okay? So that would be step number 2. Is there some place I can send you for that? Well, yeah, a little further trip, I might add. But if you go to East Africa, there's the East African Rift. It starts up in Ethiopia, extends down to Mozambique, and is pulling apart. Right now, for example, it is active, lots of volcanic activity going on there. And if it continues now, again, the big if, the part to the east will eventually pull off and become a very large island sitting off the east coast of Africa, just like Madagascar is. Now, Madagascar is much smaller, but it formed in exactly the same way.